This video is about the expansion of space and the first principles of physics that apply for calculating it. If you are a physicist or a cosmologist, you might want to skip to a shorter, more technical version of this, which is the next video. So the first principle is the expansion of space. And we're going to visualize that using two examples. One, a balloon that expands. So if the balloon, we think of the balloon as the universe with markings on the surface of the balloon representing galaxies, then as the balloon expands, the distance between the galaxies also expands. Now, the galaxies are marked by positions of longitude and latitude, and they stay at the same position as the balloon expands. If we draw that on a flat diagram, we can look at it this way. Here's an area of space with two objects, like galaxies. As the space expands, the objects retain their position on the grid lines, but their distance between them also expands as the space expands. And of course, these two objects could be the Earth and some distant galaxy. Now, are there any objects in space where the distance does not expand as the space expands? Well, it turns out there are a whole bunch of them. Here are two examples. This is a meter stick that occupies a certain amount of space. As the space expands due to the expansion of space, like this, the meter stick does not expand to fill that space because it's being held together by electroweak forces. The length might change, well, it does change a little bit until the forces balance out, but for our purposes, we can take it that the meter stick doesn't change in length, but the space occupied by the meter stick has expanded. And in fact, that's how we can actually, and why we can measure that space is longer. Here's another example. Here's a bunch of stars forming or in a galaxy where they're all being held in their current locations by gravity. As space expands, these stars don't get farther apart. They're still held in their relative positions by the local gravity. Now, what about light? So here's a packet of light of a certain wavelength that occupies a certain space. Currently accepted physics says that as this space expands, the packet of light and the wavelength of the light also expands, and the wavelength of the light gets longer. Now this is the cosmological redshift. So here's a packet of light being measured by a meter stick. Then as space expands, the meter stick stays the same length, but the wavelength of light expands with the space as the space expands. Now we can represent a galaxy and the Earth at a point in time, and we measure the distance by laying out a number of meter sticks all along. Here are the meter sticks that measure the distance at one point in time. Now, when a light packet leaves the galaxy and starts traveling towards the Earth, for the first portion of its travel, space hasn't had time to expand very much. So the space is still more or less the same length as the meter stick. But as time goes on, because time is passing, space is expanding more and more and more. So we can see why there must be a cosmologic redshift happening by looking at this diagram. Here's the galaxy. At the beginning, the light occupies a segment of space and has a certain wavelength. As the light travels to Earth, each segment of space has expanded and the wavelength of the light has lengthened. So when it's observed at Earth, it's observed with a redshift caused by the expansion of space during the time of travel. The last thing we can see from this diagram is that this represents the distance that the light has traveled. In other words, dl, the distance the light traveled, is made up of a bunch of segments of space that got longer as time passed during the travel of the light. And that's an important thing to bear in mind. So, we see here from first principles there must be a cosmological redshift effect playing a role in the redshift of the light that's observed on Earth.